Okay, differential equations. What is it? Well, it's plainly just equations where you have derivatives. So if you have y prime equal to x, that's an equation, right? You see an equal sign, so that's an equation. And I see a derivative, so that's a differential equation. And we even know how to solve it. How would you solve it? If a function's derivative is x, what is this function y? Y equal to what? 1/2? What?
X squared.
X squared plus
C.
c. Okay. Simple, right? So maybe we know differential equations after all. So should we finish?
Yeah.
All right. Well, it's going to be much more complicated than this. All right. Now, often what you will be given is not just a differential equation, but with another additional condition called an initial condition. So say y of 1 is 2. If you have something like this, which we call initial condition, then in the solution, not only you have this, but you also have to satisfy this requirement, which says 2 is y of 1. That's 1/2 times 1 squared plus c, isn't it? If you replace x by 1, see, y is a function of x. So this doesn't mean y times 1. This is y, where as a function of x value is substituted by 1, right? So if you want to know what y of 1 is given this formula, you would replace x by 1. That's what I did over here. And then that's 1/2 plus c, and that has to equal 2. Therefore, c is equal to 2 minus 1/2, which is 4 minus 1/2, which is 7/2. And therefore, the final answer for this equation will be y equals to 1/2 x squared plus 7/2, because we found out that c is 7/2. I replaced the c by 7/2. So that's how you solve an initial value problem. Which, by the way, is something that you've done in Calc 1 or 2. Such a question where you can solve it by just integrating the right side is called direct integration problem, because you can just solve it by directly integrating both sides. And those are the easiest type of differential equations. So let me show you another example. Let's say example 1. Solve by direct integration. Where you have y prime equals to and y of 1 is let's try to solve this question. Now, this isn't anything new. You've learned how to solve questions like this in Calculus 2. However, I intentionally made the integral hard because in order to successfully complete this course, you have to remember all the integration methods that you learned in Calculus 2. So, for example, in order to integrate this, you need something called partial fractions. And I know that you haven't been doing partial fractions for more than one semester, almost a year. So it will be quite challenging for you. And my suggestion is, if your integration skills are rusty, then go back to your calculus textbook and study it. Okay? Make sure you review everything so that everything is fresh to you again. Okay? Or else, when I solve these questions, it will be just completely inaccessible to you. Okay? All right, so let's try this. Solution. We integrate both sides, so we know that y itself is integral see, if you integrate y prime, it's y, because you're finding the antiderivative of y prime, so that's y. This one, however, requires something called partial fraction expansion. Right, so do you remember how to do such a thing? It's first you factor the bottom. And then for each factor, you put something over it, right? So for this factor here, you put one fraction. For this second factor, you put another fraction. For the case where you have a first order polynomial in the denominator, you just put one letter. If you have a second order polynomial in the denominator, you have to put bx plus c, just like this. And then you have to figure out what a, b, and c are. That satisfies, that's equal to this. Do you remember this?
Yeah.
Have you done this in Calc 2? Kind of, right? Okay. So let's actually try to remember, figure out what a and b are, a, b, c, and r. Okay, so you probably have learned to do this in many different methods, but the one I like to do is to multiply the denominator to the right side so that you don't have any denominators anymore. So if I multiply this to the right side, I have 3. When you multiply this to the first fraction, x and x cancels, and you know what? Let me actually spell these out, because I know that some people are nervous about this algebra. So let me actually explicitly write out what I'm trying to do here. So see what I did? I multiplied x times x squared plus 1 to every term in the equation. If I do that, then I can cancel everything here with this. So only 3 remains. And this x will be canceled with this x. And this x squared plus 1 will be canceled with this x squared plus 1, leaving you with a times x squared plus 1 plus bx plus c multiplied by x. This time I actually showed you all what I did algebraically, but often what I'll do is I'm just going to start from here and say I'm multiplying this to the right side and then jump from here to there. Okay? And you should be able to understand what I did here. Okay? Yeah. Because it's always the same thing. Whatever you have in the left side, the denominator, the entire denominator gets multiplied to the right side so that you only have the numerator on the left side. And you have to think about what cancels when this gets multiplied to each of these terms. Okay? So that's what you get. And then, I'm saying this because later on in this class, we will be doing this kind of calculation more intensively. It will be much more complicated. Right now, in the beginning, I might throw in something easier, but you will have to prepare for that later part. Okay. All right, so I can now multiply this out multiply everything else, I have ax squared plus a bx squared plus cx, so that I can see which terms can be combined. See, I'm thinking of a, b, c as some constants, and therefore, even if these are not like terms, if you view a as a variable, these two are now considered as like terms because a and b are some numbers, okay? So now that tells us that 3 is equal to a plus b x squared plus cx plus a if you organize it in the powers of x. Okay. All right, let's continue on. Okay, so we have, I'll just copy this one more time. A plus b, x squared plus c, x plus a. Okay, so we have this. And what we have here is not an equation in x. This is not an equation in x, although it looks like it. It's a functional equation, meaning that for any value of x, these two should give you exact same values. Okay? There's a difference. I'm not saying this is, you don't solve this for x. That's not what it's saying. This equivalence here is, it's a functional equivalence. The function on the left side and the function on the right side has to be exactly the same thing. That means whatever x is, whether x is 1 or 2 or 3 or whatever, that you should always produce the same output. Okay? And therefore, because this equation came from this one, this is still a functional equivalence. Okay? And for these two sides to be exactly same functions, you have to you have a theorem that says if you have two polynomials and they're exactly the same, then their coefficients must match. So you have to think of this 3 on the left side as 0x squared plus 0x plus 3 equal to a plus b x squared plus cx plus a, so that a plus b has to match with 0, c has to match with 0, and a should match with 3. So we have a equal to 3, c equal to 0, and a plus b also equal to 0. a 3, c 0, this should be 0. Okay. And because b is equal to negative a and a is equal to 3, we have negative 3. Okay? All right. Now what does that give us? Well, it gives us the following identity. It says that 3 over x squared plus 1 is equal to 3 over x plus negative 3x plus 0 over x squared plus 1. Any questions so far? Now, if you're curious to know if this is really true, you can check by actually combining these two fractions into one. How do you combine two fractions into one? You make common denominators, right? So let's just do a check. Check. Multiply, for the first one, I'll multiply x squared plus 1. And for the second one, I will multiply x top and bottom. So now I have common denominators, right? What do I get on the top? This is 3x squared plus 3, and that's minus 3x squared. And because I have common denominators, I can just write it once for all. And do you see that these two cancel? What are you left with? 3 over x times x squared plus 1, exactly the same thing as that, right? So indeed, what we figured out was that these two sides are functionally equivalent. They're same functions. Therefore, whether you integrate this function or whether you integrate this function, it doesn't matter. It's the same thing. Okay? Any questions so far? Good? All right. Therefore, now we can go back and do the integral where this function is now replaced by that one. you have integration of 3 over x minus 3 times x, x squared plus 1 dx. Okay. In Calculus 2, you also learned something called u substitution. And that's what you need in order to integrate the second part. You want to take u equals x squared plus 1 to integrate. So let me just calculate the integral of this part only using u substitution here. Let's see. Integral of x over x squared plus 1 dx. You do this by first setting u equal to x squared plus 1. du equals to 2x dx. And after you do this, you solve for dx, right? So dx is 1 over 2u du. Sorry, 1 over 2x du. And now you can substitute x squared plus 1 by u, and dx can be replaced by 1 over 2x du. And that makes this integral as integral of x over u times 1 over 2x du. X cancels, and you're integrating 1/2 of 1 over u du. What's the integral of 1 over u? What's the integral of 1 over u?
ln of u.
ln of u, thank you. So this is 1/2 ln of absolute value of u plus c, and because u is equal to x squared plus 1, that becomes 1/2 ln of x squared plus 1. And at this point, I can just drop the absolute value sign because x squared plus 1 is always positive. So that's what we need, and therefore we have the integral here as this is 3 times 1 over x, so that's 3 times ln of x minus 3 times ln of x squared plus 1. Oh, by the way, this should be 3 over 2. Sorry, there's a 1/2 here. I should put that here. And then plus c. Now we're still not done yet because there is this initial condition which you have to apply. So you should apply this. All right, so let's see. What's y of 1? Y of 1 is 3 times ln of 1 minus 3 over 2 ln of 1 plus 1, that's 2, plus c. And that has to equal to 0. That's what they want. All right. Can you tell me what ln of 1 is? What's ln of 1?
0.
0. ln of 1 is 0 because ln 1 is e to the 0th power. So and ln is log base e, so log e cancels e and leaves you with 0. So this is a 0. This you can't do anything about it. So that just goes away, and if you solve for c, you get c equals to 3 over 2 ln of 2. Therefore, the final answer is, I'll write the answer here. The final answer is y is equal to 3 ln of x minus 3 over 2 ln of x squared plus 1 plus 3 over 2 ln of 2. So that's the answer. Do you have any questions on this? Should I explain any parts again? Okay, so hopefully this gave you strong motivation to review all your integrals, because there's certainly a lot to be reviewed. What I didn't touch here is integration by parts. I'll try to do another example using integration by parts, but not on this one. We'll do integration by parts in some other example.